Hello everyone, I would like to briefly present one of our recent papers entitled Self-Supervised Learning with Adaptive Distillation for Hyperspectral Image Classification. A hyperspectral data cube can be defined in two different domains. From the spatial domain, a hyperspectral data cube can be considered as a stack of grayscale images with different wavelength intervals. In the spectral domain, a hyperspectral data cube can be considered as a concatenation of n pixel vectors, and n shows the number of pixels, and the length of each vector is equal to the number of bands or spectral channels. It turns out that most of the approaches which have been developed for RGB images are not applicable to hyperspectral images due to the so-called curse of dimensionality or Hughes phenomena. On the one hand, the high dimensionality of these datasets increases the number of trainable parameters considerably in conventional neural networks. On the other hand, the collection of training data in remote sensing is always expensive and time-consuming. This is the main reason why there is usually no balance between the number of trainable parameters and the number of training samples. To solve this problem, a self-supervised learning method with adaptive distillation is proposed to train the deep neural network with extensive unlabeled samples. The proposed method consists of two modules: 3D transformation on hyperspectral image cubes and adaptive knowledge distillation with spectral and spatial similarities. The self-supervised learning with 3D transformation rotates the hyperspectral image cube in both spectral and spatial domains to fully exploit the labeled samples. In order to realize the geometric transformation in spectral and spatial domains, a novel fully convolutional neural network called progressive convolutional network is designed. The self-supervised learning with adaptive knowledge distillation mainly includes the following three steps. First, the similarity between unlabeled samples and object classes in hyperspectral images is generated based on the spectral and spatial joint distance between unlabeled samples and labeled samples. Second, the adaptive soft label of each unlabeled sample is generated to measure the probability that the unlabeled sample belongs to each object class. And third, progressive convolutional network is trained by minimizing the cross entropy between the adaptive soft labels and the probabilities generated by the forward propagation of the progressive convolutional network. The proposed approach was applied to multiple hyperspectral images, and it could improve several benchmark methods like 2D CNN and 3D CNN, as well as several state-of-the-art approaches in terms of classification accuracies. Thank you.